Good afternoon. This is presentation for student S400-3953 for VP Task 3A, structural analysis. We've got a table of contents. So, introduction. This basically outlines what the task has been throughout the semester for this course. For example, determining the loadings, etc., this type of stuff. Also, it's mainly going to be talking about the calculations for the VP task 3, which is finding the bending stress, shear stress, maximum principal stress, and the failure planes. And you take the loading conditions from VP task 2. So yeah, VP task 1, students were asked to find a structure they wanted to analyze, given that Dr. Sri approves of it, as you can see over here. Mine has been approved. So yeah, I went and chose this structure. It's in front of a local library in the southeast suburbs in Melbourne. And as you can see, that the length is 2.95. This is the cross section, 100 across, 150 up. And then in VP task 2, using the same beam, students were asked to calculate the shear force and bending moment diagrams, given that the loading conditions were found using students' unique student numbers. So it will be the last digit multiplied by 3.36, and then the length at which this applies will be 0.6 times by the total length of the beam. And then from here, I've calculated the shear force diagram, bending moment diagram, as well as the deflection and slope. And VP task 3, also keep in mind that in VP task 2, I didn't specify my max theta, where I lost a mark, so I've made sure to include it here. To begin with VP task 3, students were asked to calculate the maximum tensile strength for their profile, as well as the maximum shear stress, and then the calculation, the maximum principal stresses and the maximum in-plane shear stress, and then calculating the failure plane. So to begin my calculations, I started with calculating the maximum tensile or compressive stress using the equation sigma is equal to my over I, taking moment from VP task 2 to be the maximum moment, which was 7.737 kilonewton meter converted to Newton millimeter, and from here I got 20.632 megapascal. Keep in mind that due to the symmetry of the shape, the compression at the top will be equal to the tension at the bottom. So the maximum bending stress for this one would be 20.6 megapascal. I've rounded it up to 20.6 megapascal, and I've done a stress distribution graph at the bottom. To calculate the maximum shear stress, I've used tau is equal to shear over 2 times y moment of inertia, all multiplied by the height over 4, take away y1 squared, where y1 is the distance between the neutral axis to the point of interest. And from here, I've calculated that the maximum shear stress occurs during along the line of neutral axis, which for my one turned out to be 1.25 megapascal, and I've done a stress distribution graph at the bottom over here. And then to calculate the principal stresses, I've taken 3 different scenarios. One where there is maximum shear, where there's maximum moment, and then there's a combination of both. And for all these 3 different cases, I've calculated the shear and the shear stress and bending stress. And from here, I can very easily see that case 2 will give me the maximum ratio, taking that the allowable shear ratio is 400 megapascal. So from there, I've taken that to be the maximum shear, and I'm going to be using case 2 for all of the calculations, which I'm going to be doing. So yeah, and I went on to calculate my principal stresses, the maximum, using this formula. sigma 1 and 2 is equal to sigma x plus sigma y. Keep in mind that sigma y is 0 for all of the cases for this assignment. So yeah, that divided by 2 plus minus the square root of sigma x plus sigma y squared on 2 plus tau xy squared. And from here I was able to get my maximum principal stress to be 20.6 megapascal. And then I found the angle at which this acts, and it's 0 and 90 degrees. And then I did the same for the max in plane shear stress using this formula down here, and that turned out to be 10.32 megapascal. So and then I went on to calculate my failure planes. So the sigma x dash, sigma y dash, and tau x dash y dash, taking all of these values to be from the second case. And then from there I was able to calculate where my failure plane would be, and the failure plane would be at 1.239 along the beam at the bottom of it, at the bottom surface, and it will act at 0 degrees. And below that I've included my conclusion and the references. By the way, I've used online resources, however I have not used them for my calculation, but rather as a guidance. So yeah, I appreciate your